Swayam Prabha. Digital India. Educated India.
Friends, welcome you again to this class of hydraulic model. In fact, we have already done one class on hydraulic model. There basically we did discuss about dimensional analysis, and we could see that how dimensional analysis help us in getting more idea about some of the equations that we are using. Of course, in our inter classes of hydraulics, we have discussed different equations in different chapter, in different topics, and through dimensional analysis we can have a better understanding of some of those equations. Well, for example, we were discussing in the last class that coefficient of discharge, suppose CD. Well, when we study flow through orifice, we can otherwise also get that discharge Q is equal to say area of the orifice multiplied by root over 2gh, which in fact is representing velocity, and that we need to multiply by some coefficient of discharge to get the actual discharge. But there, if we go by that, we do not understand much about on which what are the parameter on which this coefficient of discharge is depending. But in the last class we explained, we discussed, and we could see that how this coefficient of discharge is depending on different parameters that we could get from dimensional analysis. So that way we were discussing about dimensional analysis in the last class, and then we could see we were discussing about some of the very important dimensionless number like Froude number, Reynolds number, and Weber number, and Mach number, and then Newton number is another. So those numbers we were discussing, and so in hydraulic model study these numbers we'll have to have a better understanding when we go for hydraulic model study. And now in this discussion, today's discussion, we will be starting with hydraulic models. First, let us see that what we mean by hydraulic model and where we actually require hydraulic model. Well, hydraulic structures or machines. Well, in hydraulic engineering we can have hydraulic structure, and also we can have hydraulic machine structures like say dam, barrage, different type of structure we can have, say spillway, culvert, all these are hydraulic structure. We are not discussing about those structures in detail here. Various cross drainage work can be there, say one canal is coming, then another river is going, now canal need to cross the river, then we can have some cross drainage work. So that is also one hydraulic structure, and those topics are of course interesting but beyond the scope of this particular subject. But that way what I want to emphasize at this point, that we do a lot of work by applying our hydraulics in design of those hydraulic structures. Similarly, we have hydraulic machines like pumps, turbine, all those we have heard, but I mean we do work with all those different important machines. Well, so hydraulic structures or machines are generally designed on the basis of available theoretical knowledge on the subject. Now, we have some theoretical knowledge of hydraulics, then how the water will be flowing through these different structures or machines. So, from our basic knowledge of hydraulics, theoretical knowledge of hydraulics, we can always design this structure. Say opening of a opening of a weir or say a barrage we are constructing, what should be the, or say bridge we are constructing, what should be the waterway, those things we can say design from our basis of theoretical knowledge. But it may not always possible to have a complete understanding of all the physical processes in a particular phenomenon. Physical processes are there and different components are interacting, different quantities are interacting, and then to have a proper understanding or exact understanding of all these interactions may not be possible. Then if our theoretical only our theoretical knowledge we apply and we design, this design may not be successful. So, for design of important hydraulic structure, if the design fails, then if it has some consequence, very important consequence, then for those important structure, for design of important hydraulic structures or machines, it becomes necessary to carry out model study. So, there the questions of conducting model study is coming. Well, that we need to that means for those phenomena where we do not have very clear analytical understanding, that there, suppose scouring problem. Well, we did discuss about scouring earlier in the canal design, but say it is very difficult to have a very clear cut understanding or to develop a very theoretical relationship for these things, and then in those issues we need to go for model study to have a better understanding, right. Then let us classify the models. Well, where we are talking about model study, then what sort of model we can have? Well, so hydraulic models can broadly be classified into three categories. One, we can talk about say physical model. Well, physical model means in the laboratory we are just producing a replica of the actual things in the field, and the actual one we call as prototype, and what we are making in the laboratory we call as model. Okay, we will be coming to that. So, that sort of model we call as physical model. Then of course, there can be mathematical model, which is becoming now very popular. Well, why it is becoming popular? Advent of digital computer, high speed computer is making it popular. So, we can express very complex phenomenon. Suppose for expressing a physical phenomenon, the mathematical expression may become very complex, and solution of that equation may sometimes become very problematic, but now we can solve those numerically. And of course, numerical solution without computer is not possible. It will be very, lot of small steps of calculations are required, and that will make it problem. But with computer we can solve those equations very easily, and that's why nowadays mathematical model is becoming very much popular. Of course, they have some limitation, physical model as well as mathematical model. Then another type of model that we can have is analog model. Well, in fact, in a class when we were discussing about pipe flow, pipe network analysis, then we did discuss about that point. That is, one tried to solve the pipe network problem, rather he solved the pipe network problem using electrical analogy. Well, because the flow around a closed pipe loop, the head loss is equal to 0. Then similar condition we can have in electrical circuit. If it is a closed circuit, the same condition we can have. So, if we have a better understanding of the electrical system, then we can use that concept for solving a problem of pipe network. So, in hydraulics engineering, sometimes you can use the concept of a phenomenon for which we have better understanding already, and using the analogy between these two systems, we can have solution of which is less familiar. We can get the solution for a less familiar system using the knowledge of a more familiar system, and that way, say for constructing flow net in hydraulic, for constructing, that means when flow through porous media we did discuss, then flow net is very important object. So, for constructing flow net, or say for in pipe network analysis, for different phenomena we can have analog model. Well, so these are very broad classification. Then what is physical model? Of course, our interest will be more in physical model in this particular subject. We will of course give a brief introduction to analog, not analog model, this mathematical model which is used, but we will be concentrating more on physical model in this particular subject. Well, so what is physical model? Physical model refers to making of a replica of the prototype, but maintaining similar condition in the model and the prototype. Suppose for many a time in our house itself, we can see someone is constructing a model of a house for decoration. Well, say a bird, model of a bird someone is making, or something, that sort of model people keep on making. Now, whether this we can call as model in true sense for our engineering purpose? Definitely not. So, this model will have to satisfy some of the condition, or it will have to have similar condition as that of the actual field. Well, the field which is the actual one, that we call as prototype, and what we are making replica of that we call as model. Well, so we need to have similarity between this model and the prototype. Now, when we say similarity, what sort of similarity? Well, there can be different type of similarity between the model and the prototype. Rather, we need to maintain different type of similarity based on our need. Well, so those similarity are, say, similarity is maintained in, first is geometric parameter. Well, geometric parameters means the dimension. Say in the model, suppose we are making a model of a spillway, then the dimension of the model, the dimension of the spillway, the length of the spillway in the prototype and the length of the spillway in the model must be proportional. That means the length of every part, each and every part of the model and prototype must be in the same proportion. Well, suppose we are making the width of the spillway, when we are making width of the spillway is suppose 100, well, 100 may be too large. Suppose width of the spillway in the actual field is suppose 20 meter, and in the model suppose we are making it 20 centimeter, and then depth is suppose, our height of the spillway is suppose our say 40 meter, then here in model the depth or height of the spillway will have to be 40 millimeter or 40 centimeter. So, that means if we are maintaining a ratio of say 1:1000 in prototype, then in every part that ratio must be maintained, or say 1:100 if we are maintaining, if it is from meter to centimeter we are taking. So, suppose 1:100 we are maintaining, then at each and every part we will have to maintain that length ratio. Similarly, area we can talk about, say area, particular area, whatever we are getting in model and prototype, that ratio must be maintained. In a sense what we can say, that if we maintain those things, then ultimately geometrically, shape wise, the model and prototype will be looking alike, but the model may be smaller in dimension than the prototype. Well, why I am using the term maybe? Because generally we have a concept that model will always be smaller than the prototype, but it may not always be the case. In some case, the model may be bigger than the prototype. Suppose we are trying to understand some of the phenomenon for which we require a bigger dimension than the model, then we may go for a bigger size model also. Of course, in hydraulic engineering normally our model will be of smaller size than that of the prototype. Well, so this is basically called geometric similarity, and then kinematic similarity, that is the similarity we call as kinematic similarity. So, well, we are writing here geometric parameters, that means similarity of geometric parameter, that is we call as a geometric similarity. Then similarity of kinematic parameters, like say kinematic parameters means velocity, acceleration, these are say kinematic parameter, discharge, and then say in the model we have some discharge, or say in the actual field we have some discharge or some velocity, then the model will have to apply or we will have to put the proportional discharge. And of course, further finer things are there which we will be discussing later, but the similarity of discharge or similarity of velocity, similarity of acceleration in model and prototype, that we call that kinematic similarity. Well, in a model, that means we need to maintain geometric similarity, and in some model we need to maintain kinematic similarity. Of course, to have kinematic similarity we will have to have geometric similarity first. Well, then we are coming about another similarity that is called dynamic similarity, or we call this similarity in dynamic parameters, and that is of course for hydraulic model study very important. So, dynamic parameter means we are talking about the force. Say in a hydraulic problem where say gravitational force is very significant, then the gravitational force that is exerted or that is exerting in the prototype axial field must be same as that of the in the prototype. But how we will judge that point? That is why in that point we use those dimensionless parameter like Froude number. So, Froude number of the model and Froude number of the prototype we try to make similar. Then we can say that yes, this dynamic similarity is maintained. But of course, it is not that in all the model this gravity force will be only dominating. Sometimes it may have viscous force. Then we know that there is a dimensionless parameter which is giving the idea of the viscous force, that is Reynolds number. Well, it's a ratio of inertia force to viscous force, that Reynolds number. Then we can go for in a problem where say viscosity is more important, in those problem we can go for similarity of Reynolds number. So, in that process we try to maintain dynamic similarity. Well, now to define it, say what is geometric similarity, we can say that geometric similarity refers to similarity of sizes between model and the prototype. And similarity of size, how we can maintain? We will have to maintain some ratio, we will have to maintain some ratio. So, say if we try to maintain a ratio between length of the model and length of the prototype, that means we will have to maintain a scale between model and the prototype. That scale we call as geometric scale. So, that geometric scale we will have to maintain. So, what will be that geometric scale or what will be that ratio, that say length of the model and length of the prototype we call as length ratio. Well, so if we want to design or if we want to make a model, first we need to decide that what will be our length ratio of the model. Then of course, from that length ratio, if we want to talk in terms of area, suppose in a particular model area is very important, then we can say that okay, area of this and area of that model and prototype will have to maintain a ratio. So, if we are maintaining length ratio, then what will be the ratio of area? Definitely we can say that area of model and area of prototype, if we take the ratio, it will be say length ratio square, because area is nothing but Lm square and this is say Lp square. So, finally, the ratio will be, if we know the length ratio, we can find what will be the area ratio, that is say length ratio square. Similarly, Vm by Vp is equal to, say we can, this is volume, so we can say it is length ratio to the power cube. Well, and as explained, say L, A, V, this represents length, area and volume, and the suffix m and p that we are writing for model and the prototype. Okay. Well, then we talk about kinematic similarity. Well, so now what is kinematic similarity? We can write that to have kinematic similarity, apart from the geometric similarity, there must be similarity of kinematic parameters. That means, to have kinematic similarity, geometric similarity must be satisfied. So, that is a prerequisite. I mean, just satisfying the similarity of acceleration, velocity, which are kinematic parameter, we cannot achieve kinematic similarity if the geometric similarity is not satisfied. So, this is just a prerequisite for having kinematic similarity. Well, so geometric similarity, once it is achieved, after that we will have to have similarity of kinematic parameters like say velocity, acceleration, all those. Now, here this Vm and Vp, this V is representing velocity. Of course, in the same lecture we are using V here to represent volume, do not get confused, I can make it V cut like that. So, this is volume representing, and well, then here it is actually velocity. So, velocity of the model divided by the velocity of the prototype, that is say velocity ratio. Well, so here when a model we are trying to maintain kinematic similarity, then we will have to maintain a ratio of the velocity that we call as, that we find by velocity of the model divided by velocity of the prototype. And if this is the velocity ratio, then at each corresponding point, because then in the entire model the velocity will be different at different point, and at each corresponding point means the each, suppose we are considering a point in the prototype and each corresponding point in the model, then the velocity, if we take the ratio, it will have to have this V or value. So, this is called velocity ratio. Now, once we have the velocity ratio, then, and we have length ratio already, so we can have the ratio of some other parameter like say time ratio. So, we know that time is nothing but length by velocity. So, what will be the time ratio? Time ratio is say length ratio by velocity ratio. That means, say if we are making a model which is kinematically similar, suppose we are trying to find how much distance the water will be flowing or something like that, then if we are conducting the experiment in a model, and in the model suppose we are finding this is the time requirement and it is a kinematically similar model, then that time what we are requiring in the model will not be same as the prototype. So, we need to know that if this is the time required in the model, how much time will be required in the prototype. So, that how we will be getting, say from the model and the prototype, we know already what is geometric similarity and what is kinematic similarity, what is the value, we know the length ratio and the velocity ratio. So, if we know the length ratio and velocity ratio, taking LR, that is length ratio by velocity ratio, we are getting a different ratio, that is called time ratio. So, if we get what is time ratio, which is time ratio is equal to the time of the model and time of the prototype. Well, so if we want to get the time in the prototype from the known time that we are getting from experiment in the model, we will have to multiply the time obtained in the model by the, or we will have to divide the time obtained in the model by the time ratio, then we will be getting the prototype time, or what we can write that time of the prototype is equal to time of the model divided by time ratio. So, that way we can have the time that actually will be happening in the model. And well, with the same idea, if we try to get acceleration, say we are writing as acceleration ratio, that we can get the velocity ratio divided by time ratio, and that if we simplify, it is becoming velocity ratio square divided by the length ratio. Well, because time ratio we are replacing by LR by VR. So, we are getting this expression. Similarly, suppose we are interested to know what will be the discharge in the prototype if in the experiment we are getting a discharge for the model. So, that for obtaining that we need the ratio of discharge. Well, that say we call as Qm by Qp. So, Q ratio or discharge ratio Qr. So, how we can get this? We know that volume by time is the discharge. Now, what is volume? Volume is nothing but length cube. Already we know the length ratio. So, we will have to have that length ratio cube divided by time ratio. So, if we have the time ratio value, length ratio value, then we can have this term what is Q ratio, and then in the model if we are getting a Q, then from the known value of the model we can get the value what it will be in prototype. Or in the reverse way, suppose we know that in the prototype this will be the actual object will be having this much of discharge, then to conduct the experiment how much discharge we need to put there. If the model we are developing is a kinematic similar model, the discharge that we need to provide in the model to represent the discharge of the prototype, then we can find out again utilizing this say discharge ratio. Well, so that way we can apply the concept of kinematic similarity for deciding the discharge, time, velocity, acceleration this relationship between the model and the prototype? Well, then we come to dynamic similarity. Well, now what is dynamic similarity? Here again we are writing in the form that dynamic similarity is the geometric similarity plus the kinematic similarity plus the similarity of forces. So, that means that to have dynamic similarity, similarity of force we need to maintain. That force in the model and the force in the prototype must be similar. Well, but to have this similarity, dynamic similarity, we have two prerequisites. One is that, in fact, we can summarize that to be one prerequisite, that kinematic similarity need to be maintained, because for kinematic similarity already the geometric similarity need to be maintained, or explicitly if we want to say that, we can say that for having dynamic similarity, geometric similarity need to be maintained as well as the kinematic similarity need to be maintained, and then we will have to have similarity of forces, and then combining all these we get dynamic similarity. Well, now this is very critical, because maintaining similarity of forces in the model and prototype, now we need to think about what force, because in a fluid problem, in the flow problem, there are so many forces that can influence the flow. Well, generally the forces that generally influences flow problem are inertia, then viscous force, then gravity, then pressure and surface tension. Elastic force will also be dominating if it is a pipe flow case. Well, in open channel flow, of course, elasticity may not be that much significant. Elasticity force will be coming when we will be considering the fluid to be compressible. Well, so but these forces are definitely quite significant depending on the type of problem. Of course, in some problem, if surface tension force is significant, in some problem there may be, say, pressure force is significant. Again, in some force maybe that in some problem gravity force may be significant. That way we will be discussing about that, of course. Now, there are different forces, and it is very difficult. It is difficult to maintain the similarity of all the forces in model and the prototype. Practically, if we try to maintain similarity of all the forces in model and prototype, that become almost impossible, and that way this maintaining dynamic similarity is, in true sense, we cannot have. But still, we always try to maintain the dynamic similarity by maintaining similarity of that particular force which is dominating that particular flow phenomenon or flow problem. Well, so therefore, most dominant force is taken for maintaining similarity, dynamic similarity basically we are talking about. Well, then let us see that for what sort of problem, what sort of similarity we need to maintain. Say, for a problem of open channel flow, with water as fluid. Why we are saying that water as fluid? If some open channel flow, suppose if we talk about, say, viscosity or viscous fluid, then this may not be valid. But for an open channel flow with water as fluid, the gravity force is more dominating. Well, gravity force is more dominant, and that's why we have already discussed in our last class, in our previous class, that when gravity force is dominating, the dimensionless number which represent the ratio of inertia force and gravity force, that dimensionless number is the Prout number. And always we are using that in the form of dimensionless number, because inertia is always there, and that's why for this sort of problem we need to maintain similarity of Prout number. Fine. Again, similarly, for a problem of pipe flow, in case of pipe flow, as the flow is under pressure, water is flowing under pressure, so gravity force is not that much significant, rather viscous force is significant. And if the flow, for that sort of flow, that's why if we try to make a model of pipe flow, then which similarity we will try to maintain? It is not the gravity or that means it is not the Froude number, rather we will try to maintain similarity of Reynolds number, which represent the ratio of inertia force to viscous force. Well, similarly, for a problem where say dominated by surface tension, as we know that in some problems surface tension may be dominating, there we go for similarity of Weber number. Well, if we recall our last class or previous class, then we got what is Weber number, the inertia force divided by the surface tension force. Similarly, for pressure dominated problem, we go for Euler number similarity, and for compressible elastic fluid, we go for Mach number. Well, suppose our fluid problem is fluid is elastic type, the compressible fluid, then we need to maintain similarity of this Mach number. Well, so these are some typical cases that we are just discussing here, and depending on the problem we need to decide which force, which similarity we need to maintain. Well, then application of dynamic similarity. Well, this is very, very significant. Now, for design of hydraulic structures like spillway, river flow, well, in spillway also and in river flow also, that is in problem of open channel flow, the gravity force dominates. Well, this gravity force dominates. Now, gravity force dominates means we need to, for maintaining dynamic similarity, what we need to do, we need to equate the Froude number of the model and the prototype. Well, that means, see, if I say Fr is the Froude number, then Fr of the model should be equal to Fr of the prototype. Well, now, if we take that the experiment we are conducting, the elevation of the point where we are conducting the experiment and where it is actually existing is not that much difference, then the gravity force, that is the G, we can consider same for model and the prototype. Well, now if we consider the gravity G value to be same, acceleration due to gravity, I mean, if when gravity is same, acceleration due to gravity is bound to be same. So, when G value is considered same in model and the prototype, then we can have some interesting relation from the fact that if we try to maintain Froude number similarity, then what will be happening. So, Froude number, as we know, V by root over GD. So, this is what the Froude number is. Now, in case of similarity of Froude number between model and the prototype, if I am writing this for model and this is for prototype, okay, then we can see that Vm by root over GLm is equal to Vp by root over GLP. That is, the Froude number of the prototype is equal to Froude number of the model. Fine. Then this will indicate if G and G are same, then from here we will be getting that Vm by Vp. So, Vm by Vp is equal to root over Lm by Lp. This will indicate this. Now, Vm by Vp is what? The velocity ratio. Lm by Lp is nothing but length ratio. So, root over Lm by Lp is becoming root over Lr. So, this is very important relation that we are obtaining, that is, the velocity ratio is equal to square root of length ratio. That means, suppose we are constructing a model and we are trying to maintain Froude number similarity. Then in the model, first we are taking a length ratio, and according to the length ratio we are sizing our model, means we are shaping the model and maintaining the length ratio what we are deciding. Okay. So, that way we have make the model. Then we need to flow, we need to suppose it is a flow problem, definitely we are discussing about flow problem only. Then say water is flowing, we are allowing the water to flow in the model. Then we know that there is a velocity in the prototype, and then what velocity we will be maintaining in the model. If we maintain, if we consider or if we make the velocity ratio equal to square root of length ratio, and if we are maintaining the velocity in that form, that means we are ensuring that similarity of Froude number is now maintained. So, that we can refer as dynamically similar model. Otherwise, if we are designing or if we are sizing the model based on a length ratio, then if we arbitrarily decide a velocity ratio and put the velocity ratio there, say whatever velocity is the prototype, then from that you make that proportion and put that velocity in the model, then it will be maintaining velocity ratio, a particular velocity ratio we are providing, it is maintaining that, length ratio is being maintained. So, that way it become kinematic similarity model of kinematic similarity. But if we put the velocity ratio, if we make the velocity ratio, here you can refer to the slide, if we make the velocity ratio equal to the root of our length ratio, and then if we are maintaining that ratio in the of velocity, then this model study can give us the things which is maintaining Froude number similarity. That means it is a dynamically similar model. Well, now let us see another case. So, we need to keep this just point that VR is equal to root over LR when we are talking about Froude number similarity. Then we need to talk about another problem. Suppose for studying flow through pipe, as explained earlier, or flow around a submerged object. Well, if our object is submerged and flow is occurring over that, flow past the submerged object, in those cases, say dominating force is the viscous force, and therefore similarity of Reynolds number is maintained or need to be maintained. If we want to maintain dynamic similarity in the model and prototype, we need to maintain similarity of Reynolds number. Okay. And if same incompressible fluid is used, then it leads to, well, we are considering same incompressible fluid means say rho value, density of the fluid, rho value is same. If it is that, then again starting from say model and prototype, okay, I am writing briefly. So, model Reynolds number is rho V L by mu of the model and rho V L by mu of the prototype. Okay. So, this will give us say L m by L p, say this L p and this is L m. So, L m by L p if it comes here, and rho is same, and that is why, and then mu and mu is same, we are using the same fluid. So, mu will be same, rho will be same, or in a sense we can call that dynamic viscosity and density is same, or indirectly you can call that kinematic viscosity mu by rho, that is the nu is same. So, if nu is same, we are just cancelling this, and then we are getting say L m by L p is equal to V p by V m. Well, what it indicates? We know that V p by V m is nothing but velocity ratio. Well, so and L m by L p is our, that means this is just reverse. One is say if it is L m by L p, say we are talking about L m by L p as length ratio, as we refer to this one, say well, we are talking about length ratio first earlier. So, say V m by V p we are talking as V r and L m by L p as length ratio. So, here what we can say, say L m by L p is length ratio, V p by V m is inverse of velocity ratio. That means, velocity and length ratio are numerically, value wise these are same, but one is reciprocal of the other. Value wise means actually V r is equal to 1 by L r. Numerically the value will not be same, we can say that it is reciprocal of other. Say if V r is 3, then this will be 1 by V r should be, if length ratio is 3, then suppose if L r is equal to 3, then V r will have to be equal to 1 by 3. Okay. So, that way we are getting a relationship between velocity ratio and length ratio. Well, now if we want to maintain the dynamic similarity of Reynolds number in the model and the prototype, then we need to, after deciding the length ratio or scale of the model, then we need to again have the velocity ratio with this value, that is just reciprocal of the length ratio we will have to take as the velocity ratio. Then only we will be finding that similarity of Reynolds number is maintained. Well, Then let us see that we have discussed if the similarity of Reynolds number we want to maintain, fine, VR will be maintaining 1 by LR. This is still simple. And if we want to make the Froude number similarity, we will be making VR is equal to root over LR. But suppose in real field there are problems where, say, we cannot say that this problem is not dominated that much by viscosity or viscous force, or we have problem, or say a problem where gravitational force is important, but at the same time viscous force is also important, and in those problems we cannot just neglect one of these, and in those cases we have more problem. Then what we will do? Say when both gravity and viscous force dominate the flow, when this both dominate the flow, one needs to maintain the similarity of both Froude number and Reynolds number. Okay. So, that is what we need to maintain, the similarity of Froude number and Reynolds number. Well, such similarity can be achieved by using different fluid in the model and prototype. Say if we are using the same fluid, then it is not possible. Of course, some other way are there, but just let us see how we maintain this sort of similarity. So, Froude number, as you can see, that Froude number similarity we can maintain by putting, say, VR is equal to root over LR, fine. And then Reynolds number similarity, we know that starting, say, from Froude number similarity we are getting this one. So, this we need to maintain, Then when you talk about Reynolds number similarity, then we have that VL by nu, this is the kinematic viscosity. Rather than writing rho VL by mu, we can write VL by nu of model is equal to VL by nu of the prototype. Well, so from that what we are getting, that is nu m by nu p, that is nu of m by nu of p is equal to V of model by V of p, that is the velocity ratio, and L of model by L of p. So, nu r is equal to what we are getting, that VR, this is velocity ratio and this is length ratio, velocity ratio into length ratio. Again, so this is the condition that we are getting for, Reynolds number similarity, but again the same model will have to satisfy the Froude number similarity. Well, if it need to satisfy the Froude number similarity, we will have to have velocity ratio is equal to root over LR. That means this is the similarity of Froude number. So, putting this VR in place of VR, if we put root over LR, then from the again Froude number similarity we are putting this expression. So, then that means we are considering both the similarity of Reynolds number as well as Froude number. This leads us to the ratio of length ratio to the power 3 by 2. Well, so what we are getting, nu r is equal to length ratio to the power 3 by 2, or other way also we can get that length ratio is equal to nu r to the power the 2 by 3, that way also we can get. Well, now from this particular expression, that is nu r is equal to, say, L r to the power 3 by 2, what it means? That means nu is the property of the fluid. So, nu r is nothing but, say, nu of the model and nu of the prototype. That means the model, the fluid of the model and fluid of the prototype must not be same, it will have to have some ratio, and that ratio is what? That length ratio, if we have already decided that this will be the scale of the model, then this length ratio to the power 3 by 2, that value will have to maintain in the fluid. In the fluid means in the value of kinematic viscosity of the fluid. So, kinematic viscosity of the model and kinematic viscosity of the prototype, that must be different. So, in the model we cannot use the same fluid, we will have to get a fluid which will be maintaining this length ratio. Well, synthetically also we can develop fluid of that ratio, this is one way. Another way, suppose, well, exactly having this ratio Lr to the power 3 by 2 in the this nu m by nu p, that is definitely difficult. So, sometimes suppose we took we can take two fluid, well, we can take two fluid that we are deciding that okay, we will be maintaining this two fluid in the model and the prototype. So, we can find out what will be the ratio of the kinematic viscosity. So, once we get this ratio, then we can size our model, then we can know that what is our length ratio. So, because length ratio we can get in that case if this ratio is fixed for a given two different fluid. Well, we know this ratio, and from that we can find out what should be our length ratio in the model and prototype. That way we can decide our length ratio later after deciding the fluid of the model, once we know the fluid of the prototype. Well, so that way we can resize our model, and then we can maintain say both kinematic both Reynolds number similarity and Froude number similarity. For a problem we will have to, for some of the problem we will have to do like that. Well, then we talk about another issue in the model, that is the distorted model. Well, because for some of the problem when we are talking about geometric similarity, we are talking about a length ratio all the time. But say length ratio if we try to maintain, that means in horizontal scale, in vertical scale, we will have to maintain the length ratio. Well, we will have to maintain the length ratio. But there may be a situation, suppose we are doing a problem, we are just modeling, trying to develop a physical model of a very big river or maybe harbor. Then say width of the river is very large, or say harbor, the horizontal extent of the entire model is very large. Then to have it in a smaller model, we may have to reduce the horizontal scale too much. Say we can make the horizontal scale 1:100. But the depth of flow may be, suppose if we talk about a river, suppose horizontal scale we are reducing to 1:100, and then we are getting a model. But the depth of flow, then according to we will have to reduce. If we put the same scale 1:100, suppose depth is 10 meter, then if we apply a scale of 1:100 in the model, we will be left with a depth of what? Say 1 centimeter if the depth is 10 meter. Okay. So, well, say not 1 centimeter, so 10 centimeter depth we will be getting. Well, now that creates problem. Okay. So, say, well, so we get this distorted model. This is say in many a time it become necessary to have distorted model. Why? Say when we talk about similarity in length or say length ratio, we are saying that the length of the model and length of the prototype is say having a particular ratio. But when we are saying the particular ratio means its horizontal length, if we talk about horizontal length, the same scale we are reducing, then vertically also we are reducing it by the same scale. Now there is a problem if our model is very big, suppose a big river like that of Brahmaputra if we have, or say sea, well, harbor we are trying to model. Then to have it in a smaller dimension, we sometimes reduce the width maybe to 1:100 scale. In that case, okay, our width wise we are reducing it, fine, we will be getting a dimension of smaller dimension and we can conduct experiment. But say with 1:100 scale, if we reduce the depth, you see depth in the river may be 10 meter, then you just imagine if we reduce it by 1:100, then the depth will be very small. Similarly in harbor, if it is very big, we are reducing the scale, horizontal scale by too much, and then vertical depth also if we reduce in that proportion, then our depth in the model may be very small. And then if we conduct experiment, then we may not get the actual result. The reason are several. One is that when we reduce the depth to too smaller depth, then some of the forces which are not that dominant in the actual field, say in a big river, well, the surface tension force is not that much dominating. But in the model, if we reduce it to a very smaller depth, then the surface tension force, which is not dominating otherwise, may become a dominating force. So that way we can face problem. Well, let us see what are the problems that we may have and how we can overcome those problems in distorted model. So, in case of physical model, it becomes difficult to construct a model with same vertical and horizontal scale in some of the cases, not in all. Then for example, for a model, I have already given it for a very large river like Brahmaputra, it becomes difficult to maintain same scale for horizontal and vertical scale. Therefore, it becomes essential to construct the model with different horizontal and vertical scale. Well, so how we do this? We construct a horizontal scale different and vertical scale different, and that makes the model distorted. Well, this is one point. Distorted means we are not maintaining the same scale in the horizontal and vertical direction. Well, then there may be another case. Similarly, distortion may arise due to use of different material in experiment. Means, say when in an experiment, suppose our bed material size, we are talking about scouring, that our bed material size is again, say suppose boulder is there and we are reducing the size. Now, to represent the boulder, if we reduce the size of the boulder by the same ratio, then the material that we will have to put, its diameter or its particle diameter may be very small, and this may not be giving the same behavior as the boulder will behave, because when we reduce the size to very small size, its entire behavior changes, frictional property, then cohesive property, everything can be different, and that distortion is also one kind of distortion. So, these sorts of model are known as distorted model, and results need to be analyzed accordingly. So, once we get a model, once we are getting the result, then if the distortion, we know that in the model there are distortion, then the result will have to be analyzed accordingly. Well, then we talk about scale effect. Almost these two are related. So, what we can see that if complete similarity is not achieved, there will be difference in result between the model and the prototype, because we are not able to have complete similarity in all the time. As we have explained that maintaining similarity of all the forces is not possible. So, that complete similarity many a time we may not achieve. Now, that is considered as scale effect. So, when complete similarity is not there, then we have this sort of problem. For example, again if we talk about the same problem, say for example, for a model of very large river like say Brahmaputra, maintaining same horizontal and vertical scale may lead to very large depth of flow. Okay. So, that is another issue, and where surface tension force will become much more dominant, and thus will change the situation of model and the prototype significantly. Well, if we maintain the same horizontal and vertical flow, then vertical scale, then that may lead to not large, rather I was speaking large last, I mean this should be that it will lead to a very small depth of flow. Yes, it will lead to a very small depth of flow, as already explained, and in that case, as I have explained already, the surface tension force may become quite significant, and this sort of things actually we refer as scale effect. Well, this is what we have spoken about the hydraulic model, and particularly we are talking about say physical model, but there can be model which we develop as mathematical model. Already we have explained what mathematical model is. So, this mathematical model we can just look as having two major components. What we mean by these two major components? That means in the process of developing and then up to implementation, we basically deal with two things. One is that these two major components, one is that governing equations. Well, what we mean by governing equations? Say first we are making the model to represent a physical phenomenon, and after understanding that physical phenomenon, we need to express the relationship of the physical parameter involved in that physical phenomenon in terms of some mathematical equation, and that equation we call as governing equation. But for a particular problem, we may not have a single equation. Like for example, say when we were talking about unsteady flow in open channel, then the governing equation we were deriving, and there are, to represent that flow, unsteady flow, we need to have two governing equation when this is one dimensional problem. That is, one is continuity equation, then another is say momentum equation or energy equation. Well, we can have three equations, continuity, momentum and energy, but when we have two unknown variable for the problem, then we will be using say two equation. It should be continuity momentum couple, or couple means two, as we are using two equations, so we are talking this as couple, or it can be continuity energy couple. Now, this governing equation, understanding of these things are very important, because in a problem where we know that suppose energy loss is quite significant, in that case we should not use a equation relating the energy of upstream equal to energy of downstream. Of course, if we know about the loss in between, then we can use energy equation, that energy at upstream minus loss is equal to energy at downstream, that we can do, but otherwise we should not. So, depending on that, we will have to have our governing equation. Then okay, in different problem we can have one equation, two equation, like that. After that, next step, once we know the governing equations, the next point is the solution of the governing equation. How we will solve the governing equation? Mathematically we can solve it, analytically if possible. If not, sometimes we go for its graphical solution. If not, sometimes we go for numerical solution. Well, now if we see that real world things are so complex that simplification of the same, that means the problem, simplification of the problem with a list of logical assumptions is always necessary. When in our all the previous classes we could see that when we are talking about derivation of some equation, we are always talking about some assumptions involved in it. So, those assumptions we are always including in the governing equation. Well, and that is why when we are using a governing equation, in physical model of course we have some problem as we have discussed, but in mathematical model also we are using those equations with some assumption, but those assumptions may not be fully valid. Well, now in most of these the cases, the mathematical expression becomes so complicated that exact solution of the governing equation become difficult. So, in that process our governing equation becomes so complicated in most of the cases that we hardly can get exact solution of the equation. Therefore, recourse is generally made to the numerical solution, because as we know now that we have discussed some of the numerical issue in our earlier classes also, and of course from our very basic mathematics we might be knowing what numerical solution means. So, that way using those numerical solution we can now get solution for say partial differential equation, we can get solved by numerical method. Well, whatever complex the equation may be, say nonlinear equation or whatever it may be, we can get solution nonlinear differential equation. Generally we found many a time we get this sort of equation in hydraulic engineering. Well, then mathematical modeling is gaining popularity nowadays, because earlier the solution of those equations were problematic. Now with the advent of digital computer, this solution is becoming quite efficient, and again people are developing with development of efficient numerical algorithm. One is that gaining popularity with two things. One is that advent of high speed digital computer, yes we have this, and with the development of efficient numerical algorithm. So, numerical solution also when we talk about, there will be always some error introduced in this, but nowadays lot of developed numerical algorithms are coming up, which is making our numerical error reduced, and they are robust. With those numerical scheme we can solve the problem for different situation. Robust means for say if we make our time space larger, or say space or time scale if we make larger, then also we can solve those equations. Some different type of schemes are there. Well, in this course we cannot go into detail of those topic, but still say we can say that governing equations mean this conservation of mass, then momentum and conservation of energy. These things can be used, and based on our need we use different combination Then we are going for numerical solution. We have discussed the numerical solution. Also, this we did mention earlier also when we were discussing about unsteady flow, that characteristic method, finite difference method, finite element method, finite volume method, all these different methods we can use. Again, suppose in this method itself, say in finite difference method, for an example, we have say explicit and implicit scheme. So, explicit scheme we can get the value of the variable directly, implicit we need iterative procedure. Well, then explicit scheme sometimes may become unstable, but implicit schemes are stable. But implicit scheme though stable may give erroneous result, but explicit scheme when it become unstable, well, we are not getting any result at all, but if we maintain the stability of the scheme, we get accurate result. So, that way some advantage, disadvantage are there. Again, in explicit scheme we can go for first order scheme, second order scheme, depending on how many term of the Taylor series we are using. Well, that sort of different things are there, which of course we do not have the scope of discussing all this in detail in this particular course. Well, but still as a just introduction we are giving this part. Then knowing that mathematical model, what we do, we take a governing equation, then we get the solution of that, and then of course with computer now we solve that problem, and the result we can develop graphically, and then that we can create animation out of that results we are getting. So, exactly how in the nature will be it will be, suppose a flow problem will be occurring, how it will be flowing, we can just simulate the same thing there in the mathematical, in the computer. So, lot of softwares are also available for solution of different type of problem. Well, now what are the advantages of mathematical model over physical model? One is that mathematical models are economic. If we want to make physical model, we need to spend lot of money, but if we want to make mathematical model, a computer if we take, if we know the algorithm very well, we can write a program and then we can get the result. So, it is not that costly. Of course, if we try to purchase the software, this may have some initial investment, but we need not purchase the software. We can develop the model ourselves if we know what is numerical technique, what are the governing equation, and of course, we need to do work for developing those sort of model. And then once developed, numerous experiment can be carried out by changing different model parameters. So, in the model, suppose in a river model, we want to see that if the width is reduced, what will happen? If the depth of flow is increased, if the discharge is increasing, how the model will behave? If we want to do it in physical model, suppose we want to see if this band is increased, then we need to reconstruct the model by making say band larger, width larger, or if we want to make the width smaller, we need to make the again reconstruct the entire model. But in mathematical model, we need not do all those things. Yeah. What we need to do is that we need to just change the value of the parameter in the model. Just in one click we can make everything change, and then we can see how the model will behave for different situations. This is one advantage. Then a mathematical model developed anywhere can be sent to a far place. Well, if say we are developing a model in IIT Guwahati, that can be sent to any other place simply through the web now. Well, so that is one great advantage. But if we develop a model in this institute, then physical model if we develop, if someone asks from say the far place, well, that we need this model, transporting that physical model if it is of bigger dimension will be a big problem. But that is not happening in case of mathematical model. We can send the code straightway, and people are sending, people are sharing their knowledge, and people are using with great advantage this mathematical model. Well, for different problem, even for reservoir operation also now we are using model, and for river model study we are using model. So, that way mathematical model people are using in a big way. Then of course, this mathematical model has some limitation. Well, some of those we have already explained, the assumption is there, stability problem is there, but we cannot say that physical model is not having any limitation. Physical model is also having limitations. So, both are having some limitation, some advantage. Well, and most important aspect in mathematical modeling is that suppose we are doing mathematical model, due to numerical problem there may be some distortion, particularly in fluid problem. Suppose surface, we are finding that somewhere some distortion in the computational profile, this sort of. Now, this sort of distortion sometimes may be due to numerical error. But one must know very deeply what the numerical problem can be, and that's why if he just do the mistake by thinking that okay, in the actual physical problem also this sort of disturbance will be there, then he will end up in doing error, in mistake. So this is very important. So the most important aspect of using mathematical model is that one must be knowledgeable enough to distinguish between the numerical distortion and the actual distortion due to physical processes in the model result. So whatever he is getting, he will have to understand. So without knowing blindly, people should not use mathematical model. Well, so he will have to be thorough about the process of development, about the governing equation. Again, in governing equation also there are different types, as we did discuss in our very beginning classes, some of our beginning classes at the beginning, say conservative form, non-conservative form, all those forms he should be very clear, and then what the numerical methods he is applying, he should be very clear about that. Then after understanding all, one should go for applying mathematical model. Well, we have discussed today about the hydraulic model. There we have seen that the model can be physical model, mathematical model, and of course it can be an analog model as well. But we have discussed more detail about only the physical model and the mathematical model. And of course, though we are saying that we have discussed in detail, this is just a preliminary discussion, we can say, on models, because to cover all the issues that are there in physical model and as well as mathematical model, it will require much more discussion. But still, with this limited time, we have tried our level best to discuss the issues of physical model and mathematical model, and we have seen that in physical model we have some limitation like, or we have some issues like distorted model or scale effect. And similarly in mathematical model, though it has lot of advantages that we have discussed here, several advantages are there, but still there we should be very much careful. If we get, suppose in a surface, water surface, we are getting some distortion, then it may be due to numerical distortion. But if we just take it as the distortion of actual physical distortion, then we may be misled by that. So in all those issues, we should be very careful. So with this, we are concluding our topic on hydraulic model. Well, and of course, not only hydraulic model, today we are concluding our entire course on hydraulics. Well, in our entire course, we have discussed several topics starting from uniform flow, non-uniform flow, hydraulic jam, and then pipe flow, then canal design. So several topics we have discussed. In all those topics, we have basically tried to give concept of the hydraulics of all those issues. In some of the topic only, we have done some numerical problem to do some exercise, but our basic intention was to give the concept. Why? Once we have the concept, then of course we can do exercise. The numerical, we can take book and we can do exercise to have expertise on those issues. Expertise means, so practically, if we do the numerical problem, then we will be gaining more understanding of those issues. But the understanding the very basic concept is more important. Once we can understand the concept, then we can, with that understanding, we can solve our actual problem in a much better way to become a good field engineer, or we can do our research in this particular field to become a good researcher. We hope that if we could explain the topic, explain the concept in a better way, then we will be able to become, if we have understood that, then we will be able to become, if we want to become an engineer, field engineer, yes, a good professional field engineer, or if we want to become a researcher, we will be able to become a good professional researcher. With that, best wishes. Thank you very much.